Hello everyone, I'm Jahnavi, Assistant Professor in the CSC department. Welcome to today's lecture on one of the most important concepts in process management, CPU scheduling algorithms. Have you ever wondered how your computer is able to play music, browse the internet and run multiple applications at the same time? How does it decide which program should the CPU use first? Don't worry, in this session, we'll answer these questions by learning about CPU scheduling algorithms. Before we begin, let's take a quick look at the topics we'll cover in this session. We'll start by understanding what CPU scheduling is, why is it essential function of the operating system. Next, we'll discuss the scheduling criteria that are used to evaluate the performance of different scheduling algorithms. We'll also be looking at the major CPU scheduling algorithms, understand how each algorithm works, and we'll also compare their characteristics. To strengthen our understanding, we will also solve numerical examples using Gantt charts and calculate important performance metrics such as waiting time, turnaround time, and response time. Finally, in this session, we will evaluate the performance of different scheduling algorithms and identify the scenarios in which each of the algorithm is most suitable. So let's begin with the first topic, what is CPU scheduling? To understand what is CPU scheduling, let's begin with a simple real-life situation. Imagine you're standing in a bank where there are 5 and there is only one cashier. Since there is only one cashier, one customer can be served at a time. And now think about it. How should the cashier decide who to serve the first? Should the customer who arrived first must be served, or should the customer with the smallest transaction be served the first so that more customers can be served quickly? Or should an elderly customer or a person with special needs should be given the priority? There isn't just one correct answer. Different banks may follow different service policies depending upon their objectives, and a computer system faces a very similar situation. For the better understanding, let's map our bank's example to the computer system. Instead of customers, we have processes waiting to execute. The cashier represents the CPU because both can serve only one task at a time. The waiting line represents the ready queue where the processes wait for the CPU allocation. Finally, the bank manager represents the CPU scheduler, which decides which customer, our case, which process should be served next. Based on this analogy, we can now define CPU scheduling. CPU scheduling is the process of selecting one process from the ready queue and allocating the CPU to it for its execution. Now that we understand what CPU scheduling is, the next question is, why do we need CPU scheduling? Let us consider a computer that is running multiple applications at the same time. For example, you may be listening to music, browsing the internet, downloading a file, and editing a document simultaneously. Although many applications appear to run at the same time, they all require CPU time to execute their instructions. Now imagine that all these processes become ready to execute at the same moment. Can the CPU execute all of them simultaneously? The answer is no. A single core CPU can execute only one process at a time. Therefore, when multiple processes are waiting, the operating system must decide which process should execute first. This decision is made by the CPU scheduler. It selects one process from the ready queue and allocates the CPU to it based upon the scheduling algorithm. As we have understood what is CPU scheduling and why is it necessary, let's move on to the scheduling criteria. Different algorithms make different decisions about which process should execute next. But how do we determine which algorithm performs better? To compare and evaluate CPU scheduling algorithms, we have a set of performance measures that are called as scheduling criteria. The following are the most used scheduling criteria for evaluating different CPU scheduling algorithms. The first is the CPU utilization. The next is throughput, turnaround time, waiting time, and response time. Although all these criteria measure the performance of a CPU scheduling algorithm, each one focus on different aspect of system performance. Let us examine them one at a time. The first scheduling criteria is CPU utilization. CPU utilization is the percentage of time the CPU remains busy executing processes instead of remaining idle. Let us understand CPU utilization with a simple example. Suppose we observe that the CPU for a total duration of 100 seconds. Out of these 100 seconds, the CPU spends 90 seconds executing the process and 10 seconds remaining idle. The CPU utilization is calculated by using the formula total time utilized by the CPU divided by CPU busy time into 100, and substituting the given values we get it as 90, which is the CPU busy time, divided by 100, which is the total time, into 100, which gives us for a 90% of utilization. Therefore, the objective of every CPU scheduling algorithm is to maximize the CPU utilization, keeping the processor busy as much as possible while minimizing the idle time. The second scheduling criterion is throughput. Throughput refers to the number of processes completed by CPU in a given period of time. In simple terms, it tells us how much work the system is able to complete within a specific duration. Let us understand this with a simple example. Suppose a computer system completes 20 processes in a minute. To calculate throughput, we divide the number of processes completed by the total time taken. Therefore, the throughput is 20 processes per minute. And the main objective of the CPU scheduling algorithms is to maximize the throughput so that more processes are completed in less time. Moving on, the next scheduling criterion is turnaround time. Turnaround time refers to the total time taken by a process from the moment it enters the system until it completes its execution. In other words, it measures how long a process takes to finish after it has arrived. Let us understand this with a real-time life example. Imagine you visited a restaurant at 10 p.m. and you have placed your order. After waiting for the food, eating your meal and completing the payment, you leave the restaurant at 10:45 p.m. The total time you spent in the restaurant is now, that is from 10 to 10:45, it goes around 45 minutes. This is similar to the turnaround time of a process. Let us consider in a computer system, a process arrives at 2 milliseconds and completes its execution at 15 milliseconds. The turnaround time is calculated by using the formula turnaround time is equal to completion time minus arrival time, and substituting the values. This means that the process has spent a total of 13 milliseconds in the system, including both the waiting time and the actual execution time. One thing we need to understand is that the turnaround time includes everything. That is the moment from which the process arrives until it finishes the execution. And the objective of any CPU scheduling algorithm must be to minimize the turnaround time so that the processes complete as quickly as possible. As we have just learned about turnaround time, which represents the total time a process spends in the system from its arrival until its completion. However, during this period, the process is not executing on CPU all the time. Before it gets CPU access, it may spend some time waiting in the ready queue. And this time spent waiting before execution is called as waiting time. Let's relate this to a hospital example. Imagine you arrived at a hospital at 10 a.m. in the morning for any doctor's appointment. Since the doctor is attending other patients, you must wait in the waiting hall for 20 minutes. At 10:20 a.m., the doctor begins your consultation. Here, the 20 minutes spent in the waiting hall is your waiting time. The consultation itself is not the part of the waiting time. Waiting time can be calculated by using the following formula. Waiting time is equals to turnaround time minus burst time. Here, the burst time represents the actual CPU execution time required by the process. Suppose a process has a turnaround time of 13 milliseconds and requires 5 milliseconds of the CPU execution time, which is going to be our burst time. Then using the above formula, the waiting time is calculated as 13 minus 5, which gives us a 8 milliseconds of waiting time. Together, the waiting time and burst time make up the total turnaround time. The goal of an efficient CPU scheduling algorithm is to minimize the waiting time so that the processes spend less time in the ready queue and more time executing. So far, we have learned how long a process waits in the ready queue and how long it takes to complete its execution. However, in many systems, especially interactive applications, users are more concerned about how quickly the system starts responding to their request rather than how long it takes to finish. This is measured using the next scheduling criterion, which is called as response time. The response time is defined as the time elapsed from the moment a process arrives in the ready queue until it is allocated the CPU for the first time. It measures how quickly a process receives its initial response from the system. Let's understand this with another simple hospital example. Suppose you have arrived at the hospital at 10 a.m. in the morning. At 10:05, the doctor calls you into the consultation rooms and start examining you. Although your treatment may continue until 10:20, the response time is only 5 minutes because that is the time that you waited before your receiving attention for the first time. In the same way, a process may continue executing later, but its response time is measured only until it gets CPU for the first time. The formula for the response time is equal to first CPU allocation time minus the arrival time. Suppose a process arrives at 1 millisecond and gets the CPU for allocation for the first time at 4 milliseconds. Using the above formula, the response time is calculated and it is measured at 3 milliseconds. This means the process waited only 3 milliseconds before it started executing for the first time. And the objective of a CPU scheduling algorithm is to minimize the response time so that the users receive quick feedback after submitting a request. So far, we have understood the different scheduling criteria used to evaluate the performance of a CPU scheduling algorithm. These criteria include CPU utilization, throughput, turnaround time, waiting time, and the response time. An ideal CPU scheduling algorithm should maximize the CPU utilization and throughput while it must minimize the turnaround time, waiting time, and response time. At the same time, it should ensure fairness among all the processes. But how does the operating system achieve these objectives? The answer lies in the CPU scheduling algorithms. These algorithms define the rules used by the CPU scheduler to decide which process should be allocated the CPU next. The most widely used CPU scheduling algorithms are first come first serve, which is also referred as FCFS, shortest job first, which is referred as SJF, priority scheduling algorithm, and round robin. Different algorithms make different decisions. Some try to reduce the waiting time while some try to improve the response time while some try to maintain fairness. In the next video, we will learn how each algorithm works with numerical examples and Gantt charts, and we will also evaluate these CPU scheduling algorithms against each of the criteria. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.